Hey everyone, so in this video I want to talk to you a little bit about binomial expansion, and based upon the things that we've been talking about, that might kind of seem like an odd topic to be kind of introducing into this portion of the chapter, but trust me, you're going to kind of see where we're going with this fairly soon. So first of all, let's remind ourselves what a binomial is. Of course, we know that a binomial is an expression with two terms. So a general binomial could be expressed as something like, say, a plus b, right? There's two terms and we're adding them together, okay? Now what we're going to be doing is we're going to be looking at various powers of this binomial. The first one we're going to do is power of 0. So we're going to take this and we're going to put it to the power of 0, and we're going to consider what happens when we expand this out. Well, of course we know that when we put anything to the power of 0, we get 1, and that's no exception here. So we just end up getting the number 1 when we put a plus b to the power of 0. Okay, so let's take a look at the next expansion. So this is where we're going to be putting a plus b to the power of 1. And of course we know that when we put anything to the power of 1, we just get the same value back. So a plus b to the power of 1 is going to be just a plus b. But I'm going to write it in a very particular way. Instead of writing a plus b, I'm going to write it as 1a plus 1b. So I'm going to show the coefficients of each of these terms. And again, this will make sense to the reason why I'm doing this fairly soon. Let's do the next power of a plus b. So that's going to be a plus b to the power of 2. Okay, so in order to expand this out, it's kind of helpful to split this up into two sets of brackets where we have a plus b times a plus b. And then of course we can use the distributive property, right? So we would do, a times a is a squared, a times b is ab, b times a is also ab, and then b times b is b squared. So we end up getting a squared plus ab plus b squared. And then I'm going to get you guys to notice that we have couple of like terms. We have ab plus ab, and of course those add together and we get 1a squared plus 2ab plus 1b squared. So again, I'm wanting to make sure that we show the coefficients even in cases where we typically wouldn't. Okay, let's take a look at another power of this binomial. So we're going to do a plus b to the power of 3. Okay, so to make this easy to expand out, well, a plus b to the power of 3, well, that's just a plus b times a plus b squared, of course. And we actually just calculated what a plus b squared is. So that means that we end up having a plus b times a squared plus 2ab plus b squared, just like we showed above. And then of course we can apply distribution to this as well. All right, so we do a times a squared, which gives us a cubed, a times 2ab, which is plus 2a squared b. Then we do a times b squared, which is plus ab squared. Then we can move on to the b term. B times a squared is just plus a squared b. B times 2ab is plus 2ab squared. And then we have b times b squared, which is plus b cubed. And of course, you're going to notice that we do have some like terms. So for example, 2a squared b right here is a like term with a squared b. And then b squared is a like term with 2ab squared. So we can kind of put those together and we end up getting 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. And again, I'm making sure to show those coefficients. Okay, so why am I showing these coefficients? If you're paying very, very close attention to what's going on here, you're going to actually notice something interesting. Take a look at let's start at the top and take a look. So the only term we end up getting for a plus b to the power of 0 is 1, which means that the only coefficient that's there is the number 1. Then for a plus b to the power of 1, we have two terms, and the coefficients are 1 and 1. For the next binomial expansion, the coefficients ended up being 1, 2, 1. And then for the one after that, we ended up getting 1, 3, 3, 1. Now these numbers might actually seem kind of familiar to you because they're actually terms in Pascal's triangle. So let me draw out Pascal's triangle really quickly here. Right, these are the first couple of rows of Pascal's triangle. Notice that the terms in each row actually correspond with the coefficients in these binomial expansions. And that's actually, once you notice it, that's actually going to make it really, really easy to expand out certain binomials because you can use this rule in a combination with a couple of other things in order to do this fairly simply. So what we can say is that in general, the coefficients of the terms in the expansion of a plus b to the power of n corresponds to terms in row n of Pascal's triangle. So the power of the binomial is actually going to correspond with the row number of Pascal's triangle that you're working with, and the coefficients that you get are going to be the terms in that row. So that's going to make it really, really easy to expand these out. Now, there's one other thing I want to kind of point out to you before we can move on, before we can actually use this rule to expand out binomials fairly simply. One thing I'm going to point out to you, I'm going to get you to take a look at say the last example we did, where we did a plus b to the power of 3. And I want you to look at the powers of a in consecutive terms. So for example, in the first term, we end up getting a to the power of 3. In the next term, we ended up getting a to the power of 2. In the next term, we ended up getting a to the power of 1. And in the last term, there's no a, so you can think of that as a to the power of 0. Now that's actually a pattern that we can use in order to expand this out as well, because the powers of a actually follow a particular rule. They start at the power of 3, which was our n in this case, so they start from the value of n, and they go down consecutively towards 0. There's also an interesting rule if you look at the powers of b. So again, let's take a look at that same example. So in the first term of the expansion of a plus b to the power of 3, I want you to notice that there is no b, there is no factor of b there. So you can think of that as being b to the power of 0. Then when you look at the next term, you end up getting b to the power of 1. In the next term, you get b to the power of 2, and in the last term, you end up getting b to the power of 3. So what you're going to notice is that the powers of b also follow a pattern, right? The powers of b, they actually start from 0, and they go up consecutively towards the power that you're working with, n. So these bits of information, both the connections to Pascal's triangle and these patterns in the powers of a and b, are going to be what are going to allow us to expand out binomials fairly quickly, right? A lot quicker than you guys used to be able to do. So tell you what, let's take a look at a particular example of how to do this. So the first example, we're going to be expanding 2x plus 1 to the power of 4 using Pascal's triangle. So we have a binomial, right, to the power of 4, and we're going to use Pascal's triangle to do this. So the fact that we're dealing with a power of 4 tells us that we are going to be working with row 4 of Pascal's triangle. So one thing that would be helpful is to actually draw out row 4. So I've drawn up to row 4 here, and notice that these are the values of the coefficients that we're going to be working with here. Okay, great. So that's great. So we know the values of the coefficients. So let's actually apply our powers of a and powers of b rule to expand this out. So we're going to be expanding out 2x plus 1 to the power of 4. Okay, so one thing I'm going to point out to you here is that we actually have, so for our a term is actually this entire piece here, this 2x. So a is 2x. So for example, when I said that we start with doing a to the power of n, right, and in that value, the power of consecutive terms goes down for a, what we're putting to the power of n for that first one is actually 2x. And likewise, our b value in this case is going to be 1. Okay, so let's apply the rules that we just talked about. So for the first term, well, our coefficient that we're going to be placing down is 1, because of course that's the first term in row 4. And then of course our a value is 2x, so that is going to be put to the power of 4, because that starts at the highest power and goes down. So we're going to have 2x to the power of 4, and then we're going to be multiplying that by our b value to the power of 0, so times 1 to the power of 0. And that should give us our first term in the expansion. So for our next term, we're going to take the next term in row 4 of Pascal's triangle. That's going to be 4. All right, and then we're going to take our a, which is 2x, and we're going to put it to the power of 3 this time, because we did just have it at 4, and we have to decrease the power by 1 each time. And then, as we said, our b value is actually going to increase in power each time we go. So we had a power of 0 in the first one, and this is going to be a power of 1. So we're going to have 1 to the power of 1. Okay, so according to Pascal's triangle, the next coefficient we're going to need is 6. Then we're going to take our a and put it to the power of 2 this time, so that's 2x to the power of 2. And we're going to be multiplying that by our b to the power of 2 in this case as well. Okay, next we are going to do, okay, so our coefficient is 4. So we're going to have plus 4 times 2x to the power of 1 times 1 to the power of 3. And then we're going to have our last coefficient, which is plus 1, times 2x to the power of 0, times 1 to the power of 4. Now I'm just going to stop here for a moment. I'm going to get you to notice one other thing. So we did say that the powers of a go down for consecutive terms, and the powers of b go up for consecutive terms. There's actually another interesting property you might be able to see here. Take a look at the powers of a and b in each of these terms, and I get you guys to notice that they actually all add up to the same number. So for example, the power of a in our first term is 4, and the power of b is 0. 4 plus 0 is, of course, 4. In the next one, we had a power of a of 3 and a power of b of 1. 3 plus 1 is also 4. The next one, we have 2 plus 2 is also 4. 1 plus 3 is 4. And then 0 plus 4 is also 4. So what's interesting here is that the powers of a and b in each term actually add up to the power that you're using to expand. Okay, so that's just one interesting property, but let's move on from here. So now what we have to do is we just have to kind of expand and simplify this a little bit. So let's see here. So for the first thing, well, I'm going to get you to notice that our coefficient of 1 in our first term, since we're multiplying by 1 doesn't really do anything. And what's more is that we also end up getting 1 to the power of 0 in that first term. And of course, 1 to the power of 0 is just 1. So we're multiplying by 1 there as well. And that means that those are actually not going to contribute anything to our answer. So we end up just getting 2x all to the power of 4, which of course is going to be 2 to the power of 4 times x to the power of 4, which is 16x to the power of 4. So that's our first term. Okay, so for the next term, well, notice that we have 1 to the power of 1 there. Again, that's just multiplying by 1, and that means that that's not really going to contribute anything. And that means we're going to have 4 times, well, 2x all cubed. Well, 2 cubed is 8, and then x cubed is, of course, just x cubed. So we get 4 times 8x cubed. Okay, so for the next one, next term, so 1 squared is 1. So multiplying by 1, again, doesn't do anything. And then, of course, we end up squaring 2x. So that ends up giving us plus 6 times 4x squared when we expand the power of 2 into 2x. For the next one, okay, 1 to the power of 3 is 1. That's not going to contribute anything. So we're going to end up getting plus 4 times 2x. And then for the last one, we have a coefficient of 1. We have 2x to the power of 0. Well, 2x to the power of 0 is just 1. And then we have 1 to the power of 4. So each of those are actually just 1. So we just end up multiplying by 1, like 4 or 3 times rather. So we end up getting 1 times 1 times 1. Well, that's just plus 1. Okay, great. So now we just have to do one last little bit of cleaning up. So let's see, we get equals to 16x to the power of 4. 4 times 8x cubed, well, that's just plus 32x cubed. 6 times 4x squared, that's plus 24x squared. And then 4 times 2x, that's plus 8x. And then, of course, we just have our plus 1. So that is actually the correct expansion of 2x plus 1 to the power of 4. And notice that that's a lot less work than just kind of manually explaining it out using the distributive property like you guys would have done in the past. Okay, so let's take a look at one more example. This time, we're going to expand x minus y to the power of 3. Well, since we're dealing with a power of 3, that means we're going to want to deal with the row 3 of Pascal's triangle. So how about we draw that out? So there's row 3 right there, and that means that those are the coefficients we're going to be using. Okay, so let's set this up. So we have x minus y to the power of 3. Now, one thing I'm going to point out here, before we said that we were expanding things in the form of a plus b to the power of n. This is not really in the form of a plus b to the power of n because we have that minus there. But we could actually force it to be in the correct form, right? So what we can do is we can express this as x plus negative y to the power of 3. And now we have that plus sign there, and it actually does take the form that we require. So in this particular case, our x serves the purpose of a, and negative y is essentially b. Okay, so now that we have that kind of out of the way, we can actually apply our rules to expand this. Okay, so our first coefficient is going to be 1. Okay, and then we want to do a to the power of 3. Well, that's going to be x to the power of 3 in this case. And then we're going to want to do b to the power of 0. That's negative y to the power of 0. Okay, so for our next term, well, our coefficient is going to be plus 3. Then we're going to have a to the power of 2 this time, and then b to the power of 1, so it's going to be negative y to the power of 1. Our next coefficient is going to be plus 3. We're going to have a to the power of 1, which gives us x to the power of 1 in this case, times b to the power of 2, that's going to be negative y to the power of 2. And then our last coefficient is going to be plus 1. And we're going to have a to the power of 0, so that's just x to the power of 0 in this case, and then b to the power of 3, which is, of course, negative y to the power of 3. So now we just have to kind of expand and simplify a little bit. All right, so let's see here. So looking at our first term, again, that coefficient of 1, since we're multiplying, that's not going to do anything. And negative y to the power of 0, well, that's just 1, so that's not going to do anything. So we end up just getting x cubed for our first term. Okay, so for our second term, we have to think about this a little bit more closely. So we end up having 3 times x squared times negative y. Well, since we're multiplying by a negative, that actually tells us that we're going to have a negative term, right? Or we're going to have a minus symbol up front. So think about what positive 3 times x squared times negative y is. Well, it's going to give us negative 3x squared y. Okay, let's take a look at the next term. All right, so let's see here. So we have positive 3 times x times negative y squared. So I want you to look at that negative y squared for a moment. Negative y squared, let's see. When I do negative y times negative y, that's just positive y squared. So you end up having 3 times x times y squared. Well, that's just plus 3xy squared. Okay, and then for the last term, that coefficient of 1 contributes nothing since it's multiplying by 1. X to the power of 0 is 1, which means it's not going to contribute anything. And then we're going to have negative y to the power of 3. Well, that's just negative y times negative y times negative y. And of course, a negative times a negative times a negative is going to be a negative, so we're going to have a negative term here as well. So we're going to end up getting negative y cubed. So this is the correct expansion for x minus y to the power of 3. Okay, so I just wanted to go through a couple of examples of how to use Pascal's triangle to do binomial expansions. I hope you guys find this helpful. Take care.